There is another type of non-competitive inhibition, which is known as a mixed type inhibition. It also falls under non-competitive inhibition. The difference is when you plot the Lineweaver-Burke plot, okay, the double reciprocal plot, then you will find that there will be no similar value in terms of Km, okay, but there is also no crossing at the similar crossing, okay, for all lines, okay, at the y-axis. Okay, so this pattern of graph, okay, it shows a mixed type inhibition where the Vm value is lower as the concentration of inhibition increasing, and the Km value is increasing as the concentration of inhibition increasing. Okay, so but still it falls under the non-competitive inhibition. Right? To find the value of Ki, okay, you can see the linear line equation of the Lineweaver-Burke equation here, and involvement of the Ki value, okay, Ki. Alright, so from this equation you may able to find the value of the Ki. Here you can see there is Kia and Kib. For mixed type inhibition, this Kia and Kib value will be different. Okay, one will be higher than another one. But for the normal type, common type of non-competitive inhibition, this Ki value, the Kia and Kib will be similar. Okay, and this common type non-competitive inhibition will involve in this subject. Okay. Alright. Next is the uncompetitive inhibition. For the uncompetitive inhibition, the inhibitor binds to the site on enzyme that becomes available only after substrate binds. So here we can see that the inhibitor binds only at the enzyme substrate complex. Okay, so I binds to ES but not to free enzyme. Okay, so inhibitor does not have a bind to the active site. So the inhibitor often does not resemble substrate in terms of the structure. So here it binds to another site other than the active site because the active site has been bound by the substrate. Okay, for the uncompetitive inhibition, you can see the pattern of the Lineweaver-Burke graph here. The lines will be parallel. Okay, so the slope will not change. Okay, but the value of K and M will be different. So Km appears lower, right? But Vm or Vmax and Kcat are equally lower, right? Therefore, specificity, there will be a specificity constant, okay? Where if you get a value of Kcat over Km, it will unchanged, right? So you can find the Vm or Vmax value from the interception at the y-axis for each of the lines, okay? And the Km value, alright, at the interception at the x-axis if you plot the graph on the graph paper. But if not, then it will be from the slope. Okay, if you're using Excel, it will be from the slope. Okay, so you can see from all the graphs, it mentioned on the Vm and Vmf or Vmax or Vmaxf and Km and Kmf. Okay, the thing is, it's only to show you that for Vmf, it is to represent the Vm for the reaction with the inhibition, okay, with the inhibitor. Same goes to the Km app, okay, in which to represent the Km value for the reaction with inhibitor, okay, but there is no difference in terms of, in order to identify, to determine the value from the graph. It's similar, okay, based on the interception, based on the slope, right? Okay, next we do have another substrate inhibition. Okay, we do have another inhibition which is called substrate inhibition. Okay, this substrate inhibition, it is caused by higher substrate concentration and it falls under uncompetitive. Okay, the main general inhibition is competitive, non-competitive and uncompetitive. Okay, but there is also an inhibition which being inhibited by the substrate, not the inhibitor. So the substrate become the inhibitor in the reaction. Okay, so what happened when you plot the Michaelis-Menten plot? Okay, you will find that, okay, you can see here, the pattern of the graph will not be a hyperbolic. It will be a curve, like a bell shape here. Alright. So if your Michaelis-Menten graph become like this, it means that there is a substrate inhibition occur in your reaction. Okay. Okay. This is a table, okay, which summarize how to determine the Ki, okay, for each of the mode or type of inhibition. You can use the linear line equation, the linear Line-Weaverberg equation, okay, but this is a table which shows a simpler way to calculate the Ki value by using the Km app and Vm app or Vmax app. Okay, the Km value for the inhibitor, the Vmax value or Vm value for the inhibitor. By using that value, you may able to calculate the Ki. Alright. Okay. So for the one without an inhibition, it will be Km app is Km, okay, and Vm app is Vm. Right. So for competitive, okay, you take the Km app value equivalent to Km, okay, 1 plus I over Ki in order to find the Ki value. Alright, in which we know that the competitive, the Vm will be similar for the one without inhibitor and the one with inhibitor. Okay, so it means here that you just take the value of Km equals to Km 1 plus I over Ki, and same goes to the other type of inhibition. Okay, for example, like non-competitive, okay, because of the Km value is similar, right? Therefore, we take the Vm app value, okay, in order to find the Ki value. So it will be, the equation will be Vm app equals to Vm, okay, over 1 plus I over Ki. Remember, Vm app is the value of Vm for the inhibition. Vm is the value for the one without inhibition. Okay. Alright. So for the uncompetitive, it seems that you can use Km app and Vm app value, either one. Okay. Okay. Next. Okay. This slide is a summary slide showing that from the Line-Weaverberg plot, we may be able to identify the type or mode of inhibition. Okay, type or mode. Okay, based on the pattern of the graph shows by the Line-Weaverberg. So, if the graph cross, okay, the line cross at the y exists, so it is a competitive inhibition. If it is a parallel, it will be uncompetitive inhibition. And if the line touch at the same point on the x-axis, it will be a competitive inhibition. This is not a mix, okay? So I just take from this side, but this is not a mix inhibition, okay? I show you just now the difference between the normal non-competitive and the mixed inhibition, okay?